Who has any questions? Maybe let's just go through the ones beginning with 2.5. Oh, you don't have a copy of them? Anybody bring a copy of the lectures? Oh, okay. Do you still have the thumb drive? Okay. Is the thumb drive here? Okay, let's see, what should we do now? Well, let me just review the logic again. Is there anybody that doesn't understand the logic of this? So this is the way that these nested else, if, and if, else, if, and else statements work. So the program comes to the if statement, the first one. It has to be inside of there is a Boolean. Right? Boolean is logic. The result of that statement can only have two values, true or false. Okay, please. So if it's true, if what's true, then it does this. If what's false, it goes to the next one. The thing that I want to make sure everybody understands is what happens at the end of this if it's true. What happens next? It goes beyond the else. It doesn't do the else. It only gets to else if everything, if all of the if, else, if all of these above are false, then it gets to else. If the first one of these it finds that's true, if it's this one, it goes from here. If this one is true, it would go from here. Okay? And there would be lots of them, remember. There's no, well, I keep saying there's no limit. I'm not sure of that. There probably is a limit. I don't know what it is, 1,000, 100. More than a normal person would ever use in a program. But there probably is some limit as to how many else ifs you can put into a statement. Sorry about the sweating. I don't know if it was gross to you. Sorry. Okay. I think I should stop after a while. Okay. Any questions about this? Yes. Closed loop, you said? Yeah, there's no simple way to go back up to this statement. From this logic. Now, there are other statements. There are, I don't know what the general name is for them. Can you get online, Alex? I don't know. Do you have web? Internet? Okay, let's go to that C++ website. Okay, so there are statements that are, the general idea is position control. That's not the exact name of it, okay? But the idea is this. You can insert names in your program as location markers. So for instance, you asked about a loop. How could I make this a loop? One thing I could do is I could put, let's say I put as a name up here, TNUT. This is a name that I'm using as a location marker. Let's just say that my logic is that if this is true, I want it to do these statements, and then I want it to go back and start over again. So at the bottom of these statements right here, I can put go to TNUT. And what that does is send it back up here before it gets to the end, which would send it down here. Okay. Now I have to be careful with this kind of logic because this is possibly an infinite loop. Right? If every time I come through here, this thing is true, then every time it goes back to TNUT, and then this is true, and then it goes back to TNUT, and it stays there forever. The program will run for the rest of our lives, or until there's a power outage or something. Okay. So be careful using this kind of logic. If you read the description in this web page, I think. Yeah, so let me find out. Has everybody looked at this web page? Yeah. This is the one I suggested the other day. I think this is really handy. So let's look at references. Oh, you got it already. Sorry. Okay. Come down to see library. And see input outputs generally these strings, time, standard definitions, variable arguments, signals, non-local jumps. Localization. Let's look at this one. Yeah, go ahead and look at it. So that shows you all of the libraries you could insert at the top. And then for each of the libraries, I'll show you in a minute, it shows you the commands that are contained inside of that library. So it's very, I think this is a really nice web page. It's like having a C++ manual. It's a little bit slow to load, but when it comes up, I'll come back to it. Okay, on that web page, if you read about these go-to statements, I think that the snobs, the programming snobs, think that that's not very sophisticated. They don't like that. But when I was a student, we used it all the time. Use that go-to. You put markers in your program to tell it where certain things are, and then at any time that the logic makes sense, you can go back to that point. Okay? In fact, there's a there's a do while statement, and you put a Boolean in here. And then somewhere down here it says end while. Again, I apologize, I'm not sure those are the exact names of the commands, but it is the correct logic. So everything inside of here gets executed, and then it goes back up here and evaluates this expression. If it's true, it goes and does this. If it's false, it goes down here. So inside of here somewhere, you need to make a change so that sooner or later, this thing is going to be false. If it's true every time, again, you're in an infinite loop. Alright, so that's the logic of the do while and the end while. And this is in the lectures that you were supposed to look at for today. But I understand you didn't get them. But lectures 2.5, 2.6, 2.7 have this, explain all this logic. But using this kind of control, you could do the exact same thing, because you could have a name here, and then you could have this same program right here, and down here you could say if, and then put the Boolean, go to, and then put the name. So this logic would accomplish the exact same thing as this logic. Because what happens here is this thing inside gets evaluated, and then if this is true, it goes back up to the name and it evaluates it again. I shouldn't say it's exactly the same though, right? There is one difference. What's the difference? Here it comes to this statement and it says do while and it evaluates it. If it's true, it does this. Then it goes back and evaluates it again. If it's true, it does it again, and so on. Until it's false. When it's false, it bypasses. Here it comes in, it does this, then it evaluates, then it does it, then it evaluates. So the difference is, this one could be false the first time, and these commands never get evaluated. But on this one, these commands are going to get evaluated the first time because you didn't check the logic yet. Right? So if you want to make this logic look exactly like that one, you have to put a Boolean up here. And then go to name 2. And put name 2 down here. So the first time through, if that's false, it's still not right, is it? So we go to name and put down here, go to name 2. So if it comes through and this is true the first time, it skips and goes to the name and then executes that. But if it's false the first time, it would go to this line which says go to name 2 and it would skip all of that. So this isn't very elegant. Everybody know that word? Elegant. What does elegant mean? Yeah, if you're talking about, elegant is often used to talk about ladies. If they have very nice clothes, nice hair, they behave very proper, we say she's elegant. But elegant is also used a lot to talk about mathematics or programming, and it's supposed to have kind of the same idea. If your program is very precise, it's put together very well, the logic is really nice, say it's elegant. This is not very elegant. Because you come here, you check something, and you go there, it's kind of haphazard. A little bit sloppy, it's more like me. Okay. Culture-specific data formats, country-specific currency systems. Okay, this isn't the one. Yeah, I don't know which one of these libraries has the let's try that one. I don't know which one has these go-to commands in it. Okay, this is getting closer. That's still not it. I don't know if there's a search button. There's not a search, is there? Trying to think of how to find it. Other than just randomly trying one library after another, which doesn't seem very efficient. Is there a search window somewhere else? Oh, at the top? No, I mean search on that website. Yeah, okay, try go to. It's 2 separate words. Yeah, lowercase is fine. You have to go. Yeah, just try and go. First of all, I said the other day there were 9 of these, right? And I made the list, so why don't I remind you of the 9? There are 9 symbols. Okay. The first one, it would be, there's no order, but you can have this symbol. It means what you think it means, less than. You can have this one. Less than or equal to. So let me just point out to you, yesterday we talked about or statements and statements, how to evaluate them. I'll just point out, you've been using them all along, right? Everybody knows what this means. This is actually an example of an or, right? Because x can be greater than 5 or it can be equal to 5. It's not the same as this. Here, x has to be greater than 5. So this has 2 possibilities, and if either of them is true, this is correct. Right? It can be greater than 5 or equal to 5, but not this. This is only greater than 5. So it's the same idea with the or in this line. So greater than, or equal to. So this one is or. This is and. I can't draw very well, but yesterday I couldn't remember this symbol. This is the one that means and. What am I up to? 6. There's one that looks like this, I think. I think it looks like this. I'm going to put a question mark because I'm not sure. Slash dot. That one? Okay. This means not equal. There's just one of these by itself. It means not, I think, right? Oh, an equal. I didn't even put equal. Probably the most common one. Equal. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, so those are the 9 Boolean operators. These are called Boolean operator. Okay? Those are all logic operators. They're not math operators. Remember we talked about that yesterday. If I write x equals to 5, this is a command. And the result of this is x is equal to 5, period. If I write x equal 5, this is not a command. This is a question. Is x equal to 5? And the result is either true or false. Okay? Any question about that? So just to reiterate again, why this is so important. Every important computer program is full of these kinds of logic decisions as it goes along, because it's full of branching. Right? Again, I use the example of a menu. You open up a menu in the top of, say, a Word document. There's 10 menus. That is the first level of branching. Underneath each menu, there's a bunch of sub choices. That's another level of branching. So just by going into those branches, you have maybe 100 different commands you could do. Everything from open a new file, change the font, make something a capital letter, new color, new page, import a graphic. Right? All of those are subroutines. Those are all separate programs. Each one of them might have hundreds or thousands of commands. And they're all pieces of a huge tree with lots of branches that goes out and out and So that's a good example of the use of logic. That's an extreme example for a lot of engineering. In a lot of engineering, you won't use that much logic. Let me give you another example from 208 that you would have to use. In 208, you might get a problem like this. Any question about the logic? I won't do the whole problem. Well, I could do the whole problem if you like. But so you draw a free body diagram. You have a normal force. In the theory that it doesn't move, there's a friction force, but it could go this way. Or it could go this way. You don't even know which way it goes. And there could be a force going, there is the force going this way, applied force. And then you have mg. So what you have to do in this case is you need to solve the two equations. Solve forces in the x direction equal to 0, forces in the y direction equal to 0. Find out what little f is. And then is little f, the absolute value of your let f, less than or equal to mu static times the normal force. Everybody agrees, that's the logic of trying to see, first of all, to see if it's moving or not. So you have to make all these calculations. Okay? So now at the end of this, the logic is, is it not moving? Is it moving? And actually, you don't even know which direction F is pointing, but now at the end of this calculation, you know which direction F is pointing. Now let's say that you find out that this is not true. That means it's moving. It's beyond the theoretical maximum static friction. So now you have to change the value of mu to mu dynamic and then calculate how it's moving. So you have three different possibilities. One is with a static force going up, one is a static force going down, the third one is a dynamic force and it's moving one way or the other. So you would need several branches to solve this simple problem with the program. Okay. Any questions about that? We'll give you lots more chances to use logic. In fact, probably for the rest of the semester, you won't write a program that doesn't have some kind of logic, some kind of at least one or two branches. Because it's actually not easy to dream a problem up that doesn't have some kind of logic. Okay. So we talked about the importance of logic. We talked about Boolean operators. My plan was, I guess it's not going to work. I was going to go through the lectures with you, just make sure you understand all the examples. The lectures are full of examples. It seems to me like the examples show what they're supposed to show, but the first time that you're seeing the material, like new students like you, it's perfectly normal if you see some things in there that don't make sense. So I thought if we went through them together, I could explain it in case you don't understand. So now I'm disappointed that we can't do that. Maybe it's worth taking a few minutes to go get the disc and come back to get the thumb drive. Yeah. I could go back to my apartment and get it, or if you know where yours is, you can go get yours. Do you know where it is? Okay. Yeah, thank you. Appreciate it. Okay, so he'll bring back the thumb drive of the lectures, and then we can go through them. And then I also just remind you that can get that web page back. We can look at some of those. That's IOF Stream, I think it's called. Or yeah. There's IO Stream, there's library, F Stream, F Stream. Yeah, I can't even remember the names of the library. While he's gone, let me tell you about something else I saw on the web this morning. I don't know if anybody else looked at this or saw this, but Sunday is the 70th birthday of the world's first electronic calculator. Okay, the world's first electronic calculator was 70 years ago. So I know that probably sounds like a long time, but your grandparents are probably 70 years old. It's not that long. Now, the world's first calculator was about 17 meters long. It weighed 5 tons. 5 tons. It cost 200,000 USD in those days. And today's, I don't know what that is, but probably something like $5 million today. And it could do multiplication, but to do a single multiplication problem took about 6 seconds. Yeah, to do one multiplication problem. Cost millions of dollars, 17 meters long. That was the world's first calculator. Okay. Now, the world's first handheld calculator. What company do you know? This is what made this company famous. This is one we've heard of. No, that's a much older company. Yeah. What's that? Well, just actually, before this question, I want to go back to the last one. So the world's first electronic calculator, 17 meters long, 5 tons, multiplication in 5 seconds, and it was IBM. Right? That's what made IBM famous. IBM built that. All right, the world's first handheld calculator. It's another, today it's a huge company that we all know about, but this was their first product. Hewlett-Packard. HP. Okay, so let me talk a little bit about section 2.9. So move ahead a little bit. 2.9 is our functions. So functions are where you can define something like, sine, cosine. There's a whole long list of them. The math functions that are already in C++, they're in the library called CMath. But you might come across some functions that you would like to have, but they don't exist yet. So you want to make your own function. Now, the idea with a function, everything you can do with a function, you can do with a do loop, or not a do loop, but a if statement. But you don't have to keep repeating over and over again. So, for instance, let's say that we always want to make a conversion from. What's a good example? Let's think of a good example. What's a function that would take multiple steps to make a calculation, but it's something we think we might want to do over and over again? Okay, I can think of one. I'm going to make a function called grade. Okay, and inside of grade, I'm going to let the grade. I'm going to read. Well, not read. Let's say CN. Is it that way or the other way? I'm terrible with syntax. It's the other way? That's right? Okay, so I'm going to input the test 1 score. then I'm going to input. That's right. Test 2 score. This is supposed to be a T. T2. Okay, so the basic idea is I'm going to make up a function, and that function is going to calculate a grade. Okay? Now, in my main program, over here in the main program, anytime I want to calculate the grade, I can use the word grade because that's the name of the function. That word now represents all of this. So just in here I can have, yeah, I don't like this. This example wasn't so interesting. I should have made it more interesting. Wow, that's the thing. Okay. Is this an example from the notes? No? It's a great example. Yeah, so this, yeah, this is good. So everybody, if you could take a look up here, let's pretend that I was clever and I had put this exact same, everything from here down to here, could go at the end of my subroutine. So first, I put in the 3 test scores, then I calculate the average, then I have this do loop to tell me what the actual grade is. So if this says test score, and let me change the name of mine to grade. So if the grade is greater than or equal to 90, then it prints out your grade is an A. If the test score, if it's greater than or equal to, I think that's, yeah, greater than or equal to 80. Right? So let's think about the logic. So for a B, normally for a B, it should be somewhere between 80 and 90. Right? So why does this logic say if it's greater than 80, it's a B? That's right. Remember the logic. If the first one is true, it does this, and then it goes down here. So it never gets to the one with 80. If the grade is above 90, it does this, then it exits that loop and comes to the bottom. But if this is false, that means it's not above 90. So it's already checked the upper side. Now it goes to the next statement, is it above 80? If this is true, then it must be between 80 and 90. Even though this logic doesn't say anything about 90, this logic already removed everything that's higher than 90. So now if it's above 80, it does this part, and then it exits and comes down here behind else. If this is false, now it can't be above 90, can't be above 80, now it does this part, is it above 70? So now this statement is really checking to see, is it in between 70 and 80? Because we already proved it's not higher than 80. Right? So now we don't have to check higher anymore, only lower. Is it higher than 70? Is it higher than 60? Right? So if all of these are false, it's not higher than 90, not higher than 80, not higher than 70, not higher than 60. The only thing that's left is it must be less than 60, so it grades out. Okay? Now this was written as a main program. also have this logic at the top of that routine. And that routine could all go in the middle here, below here. So now what it would do is it would ask for the first score, ask for the second score, ask for the third score, and you type those in. It would calculate the average. Then it would go through that same logic to see is it above 90, is it above 80, is it above 70, and print the grade. And all of that would happen in a function. So inside of our main program, somewhere in here we have a command that says grade. It's just one command. When we get to this command, it shifts the control of the program over to function grade. And it does all this. Okay, so we're going to go back. Let's look at the lectures one at a time. Can you turn the volume off so we don't hear them? Yeah. Okay.
Excuse me. So we have to write that function before we do, and then we use the rate function. Or we can use that function in another file.
You can use it, once you define a function, you can use it wherever you want. You can even use it inside of another function.
When I write program, do I have to write a function before, or I just take the function from another file that I have done
Yeah. It's an excellent
yesterday or some days ago?
Yeah, it's an excellent question. It's a very important question. So the question is, if you go to the trouble and you write a nice, beautiful function, now you want to use it not only in this program, but maybe in a bunch of other programs that you write, a lot of other ones. Do you have to put the function commands into every program? And the answer is no. That's the whole idea of that library command. So C++ comes to you with a bunch of libraries, and those libraries are full of functions that you might want to use. C math has got sine, cosine, arcsine, it's got exponent, it's got power, right? It has a bunch of math functions that are really common. Those are all each one of those functions is another C++ program. Okay? And it's in its own library, so-called library. It's like a folder. So all of those C++ programs are buried inside of C++. And if you put that include statement, and then you give the name of the library, then it puts all those into your program automatically. So you can do that with your own. So you make up your own math function. Let's say that your math function, instead of being the sine, maybe your math function is, you want to have 3 times the sine squared of the number plus 4 times the cosine squared of the number. I don't know why you want to do that, but let's say we do. So now you give this a name. Decide on the name you're going to call this. Let's call it, I don't know, my math. Okay, that's the name of the function now. You make the name. So there's already one called sine, there's already one called cosine, and so on. Now there's a new one called my math. When you call my math, what does it do? It calculates this. When it goes to calculate this, it's using sine and cosine. Those are other functions that also already exist. That's fine. One function can call another function. That's no problem. Okay? When is it useful to write a function? If you're going to use it over and over again, you might as well put it into a new name and give it a new name. Put it into its own function. Give it some name so you don't have to keep writing it all the time. If you're only going to use it once or a couple of times, maybe it doesn't matter. You just copy the statements and stick them in. Okay? Let me give you an example of another function you might want to write. I haven't started collecting homework yet, but I will. So maybe it would be really nice for you to have a standard header on all of your output files so that they look nice. So maybe on one point, maybe you have the date up here and the time, and then there's a place where you put what homework number it is, and then over on the right somewhere you've got your name, and then maybe underneath your English name. Something like that, 6 or 7 things, and you want it to look really beautiful, so some are in big fonts, some are in small fonts, maybe use color, right? These are nice over on the left-hand side, Maybe for the date, you can put a little calendar and circle the date, something fancy like that, instead of writing the date in numbers, right? So you go to the trouble, you spend 20 minutes or so, half an hour, or however long it takes, and you create a bunch of C outputs that will create this every time. And then you call that function, I don't know, homework head, or homework top. Then from now on, for the rest of the semester, every time that you have to do a program for homework, one of your commands will be to say homework top at the beginning of the output. And that way, the top of the page always looks the same. All of you have received letters, I'm sure, official letters from a business or maybe from TNUT or something, and there's a standard printed symbol of the business or symbol of the university, maybe with the return address, that kind of thing, on the top of the page. In English, we call that letterhead. Everybody knows what I'm talking about, right? You get a letter and it says, maybe it's from your bank, and it's got the bank's name and symbol on the top, and then the letter's in the middle. So you could do that. You could make up your own letterhead. So that every time you print something, it's got this beautiful symbol. You can even put a picture in there if you want. And that becomes your personal paper. So every time you print something, it's on your personal paper. You can print that paper with nothing else if you want, just the top. And keep it in a drawer, and then if you want to write somebody a letter, you can just write the letter right on top of the paper. But you can also print it automatically at the top of every other thing you print. Now, you probably know how to do this in Word. Who knows how to do this in Word? Right? You can make a standard template in Word, an output template in Word. But C++ isn't designed to produce documents. It's designed to do calculations. But it does have enough output statements that if you spend a little bit of time and play with it, you can make a very nice looking document, something like a Word document. But if you do that one time, you're going to have to do it over and over again every time. So store it in a function, and then every time you need it, you just call that function one name. You're done. That's the beauty of the function. Okay. Yeah, let's do the booleans. Okay, so here are the operators. Does anybody have any questions about these? Okay, that's kind of funny. He says easily forgotten. That was my problem yesterday. Okay, let's go to the next slide. Yeah, let's maybe hit. Yeah. Go ahead and get it. All right, let's look at the logic. So, if x is less than y, right? This is x equals 1, y equals 2, z equals 3. Is x less than y? What's the output of that? That's true, right? So a is equal to 5. If y is less than z, what's the output of that? True. So b is equal to 5. If z is greater than y, and y is greater than x. So for this to be true, because it's and, both sides have to be true. Is z greater than y? Yes. Is y greater than x? Yes, this is true. So now a is equal to 1. If z is less than y, or x is less than y, okay? Z is 3, y is 2, so z is not less than y, that's false. X less than y, x is 1 and y is 2, x less than y is true. False or true is true, so b is 1. If z is not equal to x, that's true. Z is not equal to x. B is equal to 2. So what do they become? A is 1 and B is 2. Right? A became 1 right here and B became 2. First A was 5, then B was 5, then A was 1, then B was 1, then B was 2. All of these statements are true. Now let's try this one. This shows that logic we were talking about. If y is less than x, y is 2, x is 1. False. What does the logic do? It skips this. The logic now goes to this one. Z greater than y, true. And y greater than x, also true. True and true is true. So what does the logic do? It executes this part, and then it skips down behind else. It never even looks at this. Because this is true, it does this chunk, and then from there it skips to the end and else. Okay? So this is the only part that gets calculated. A is 2 and B is 1. This part never even gets looked at. It never gets looked at. Any questions about that? Notice something about if. You can use if by itself. You don't have to put it in a loop with else if and else. You can use this with a single statement behind it. If x is less than y, then a is equal to 5. Okay? That's okay. You don't have to have an else if. The logic of this is exactly like the logic of if and only else. Right? Where there's nothing after else. So if this is true, it does this stuff. Otherwise, it comes after else and does that. Same thing here. If this is true, it does that one. Otherwise, it just goes to the next statement. So the logic of if by itself is the same as if and else with no else if in the middle. But the else if in the middle does change the logic control. Okay, let's look at the next one. Any questions about that? Should ask me. Okay, is this true or false? Can you pause it? It's too fast. Okay. X is 1, y is 2, z is 3. So we have if x is less than y, that's true. Y greater than z, false. Z greater than x, true. Y greater than x, true. X less than z, true. Y greater than z, false. So out here we have true and false. That's false. So this one gives us a false. This is true and true. This gives us a true. And this one is true and false with an and gives us a false. Now we have false, true, false with or. False or true or false. Because one of them is true, it's true. Right? These are ors. These are ands, but these are or. False or true is true. True or false is also true. Okay. Yes. Say that again. Yeah, because of the, okay, please let's have some quiet. I think this is an excellent question. Right? And when you're checking these, you have to be careful about which things you check first. So just like with the map statement, if there are parentheses, sets in parentheses, see how they're color-coded? The color is just to help you see which two go together. So these two green ones are on the inside. So you check that first. These two green ones are on the inside. Check that first. Then there's blue ones. Inside of the blue ones, you check these two together. That's the true and false. Okay, now at the highest level, there's no priority. These or statements. Okay, come on, please, quiet. These or statements are at the highest priority, and so there's three things with two or statements and no parentheses. So at this level, all three, in theory, get evaluated at the same time. Okay? But you could also think of it like the associative property of addition. It doesn't really matter. If you're going to add three numbers together, it doesn't really matter which two you add first. The third one will get added whether it's the one on the left, the one in the middle, or the one on the right. You still have the same sum. So in other words, let me write that again for you. We have false or true or false. So this is sort of like saying 3 plus 7 plus 2, right? Now, I'm going to evaluate these two things. So on the math side, if I do these two first, I get 9 plus 2. That's equal to 11. But I can also do these two first. Whoops, I didn't do that right. 3 plus 7 is 10. Plus 2, that gives me 12. I can also do these two first and add 3 plus 9, it's still 12. I could also do these two first, and 5 plus 7, it's still 12. So when I do three numbers added together, I'm going to add 2, and then I'm going to add the other one to whatever that sum is. But no matter what number I use, I always get 12. Same thing with logic, right? Let's try it. So false or true gives me true. And true or false gives me true. So that's fine. I can do it this way. True or false gives me true. False or true gives me true. Or I can do this one. These two on the outside, false or false gives me false, right? But now I have or true gives me true. So it doesn't matter which two you do first. The third one will always give you the right answer, just like this. Okay? Was that your question? You were asking me, I think, about which order you should evaluate. So let me recap my whole answer. The first part of my answer is, oops, gone now. First part of the answer is, there are a lot of parentheses. If there are parentheses, you should do what's inside the parentheses first, just like with math. Okay? If there aren't any parentheses, it doesn't matter anymore, just like this. For both or and, yeah. Okay? Yeah. But you have to be careful if you were mixing operators just like with math. It's not true that it doesn't matter anymore. 3 plus 14 is a lot different than 10 times 2. So it's the same idea here. Now, the computer has a built-in hierarchy that it decides which thing it's going to do first. In math, it usually does the multiplication first. However, you shouldn't rely on that. So if you're writing this as a math statement, if you mean this, you should put the parentheses in there so there's no question. But if you mean this, put the parentheses in so there's no question. Same idea here. Let's try this one to see what we get if we don't put parentheses. False or true is true. True and false is false. True and false is false. False or false is false. False and false is false. Or true is true. Yeah. So the parentheses, you have to know, if you mix the operators, you have to put the order correctly. Okay? Exactly the same as in math. That's I guess that doesn't help. It's not a good example. Maybe I need to make this. Yeah, actually, multiplication and division, I think it does need to work because of that. Okay, go ahead and continue on this one. Okay, so here's another control block logic example. I think it's a good one. We talked about this a little bit in class yesterday. This is the one that has to do with adjusting the units so that they look like a reasonable number. Okay? The problem with this one is that maybe it's not a problem, but the thing that might look a little bit tricky to you is I think you're not so used to using inches, feet, and yards. Right? Those are English units. Do you even know what they are? Okay. Well, roughly speaking, an inch is about 2.5 centimeters. And 1 foot in English units is equal to 12 inches. 1 yard in English units is equal to 3 feet. So that's equal to 36 inches. So in this example, he tells you to put the input in radius and height in feet. Okay, you put them in feet. So you enter the radius in feet, enter the height in feet. 1,700 versus 28 feet cubed. And feet cubed is equal to 27 yards cubed. Okay, so I used the example yesterday. If you're going to convert between meters, centimeters, millimeters, right? You divide by 1,000 for cubes, for volume. In English units, it's crazy. To convert from feet cubed to yard cubed, the conversion factor is 27. From inches to feet, the conversion factor is 1,728. So that's where those numbers come from, if you're wondering. Okay, so go ahead. Okay, so look at the logic of this. It's a good idea. This is one where the C input is going to come from the computer. So you put in the radius and you put in the height. It reads that. After it reads it, it does a check to see if you gave positive numbers. You can't have negative radius, you can't have negative height. So if either of these numbers are negative, the program will stop. If the radius is greater than or equal to 0 and the height is greater than or equal to 0. Both have to be true. If they are, then it calculates the volume. Okay. Then from there, it goes to the next statement, the next if logic, right? If the volume is less than 1, it wants to convert to a number bigger than 1. So at first it multiplies. Remember the input was in feet, so the volume has been calculated in feet. It's feet cubed. If that's too small, it should convert to inches. So it multiplies by 1,728, and that converts the volume to inches. Okay? Else if the volume is less than 27, right? If the volume is less than 27, then if it converted to yards, it would be less than 1, because the conversion factor of yards is divided by 27. So if the volume is less than 27, it stops. It says, okay, this is the volume, cubic feet. If the volume is greater than 27, it goes to this statement, another else. And now it divides the volume by 27, and this puts the volume in cubic yards. Okay, any question about that? Okay, so the next one. Yeah, you don't need this. You can do this while you're actually running this program. Yeah, we did this example yesterday, so I think you don't need to spend the time on this one. This is reading input is either yes or no. It checks to see if you put the right, if you put a legitimate Y in. So yesterday we were doing the example of color mixing. So this shows that same logic. By the way, you know what, I'm sorry, back up just a second. Look at this last question. What would happen if you entered no or in? Okay, so remember a character variable is one letter. Right? Yesterday we asked people type in your color. When we check the color, we only check for B. What happens if they type in BLUE, the whole word blue for the color? What gets stored? The first letter gets stored, so that's okay. Just you'll ignore the LUE. Okay? So a character variable has only one letter. So that would be tricky. For instance, if you're asking people for color and somebody types blue and somebody else types brown, to the computer it's the same color because it only sees the first letter. They're both B. Okay? So here's the color mix. You can look at this logic and do exercise 2.5. Okay, let's look at exercise 2.5 together. We won't finish it today, but let's look and see if we can do it. Is it? I guess nobody has seen 2.5, right? Okay. Yep. All right, tell me if you think you're ready to do this. All right, you should have done exercise exercise 2.3, that's where you calculated the pyramid volume and also the optimum cylinder. So now what he wants you to do is write a logic block to convert your units, just like the one that we just saw converted feet, yards, inches. So that's all this is, convert the units, right? And then run the two color mix examples. I think there's more on the next page. No, not that. Scroll down. I think there's, yeah. Yes, that's again. Okay. So run those two color mix ones and see what happens. Just play them. Okay, let's look at 2.6. Alright, so I've been talking a lot about the logic of ifs, else. So this is a similar logic. It's not exactly the same. It's called while. While is good for counting. Something called sentinel. What's a sentinel? What's a sentinel? Who knows what a sentinel is? Sentinel is like a guard. You know, like in a prison, there's some guy up in the tower and he's looking to see what's going on. That's the sentinel. Okay, so it's like an observer, somebody who's watching. So you use a while. You can use a while to count something. You can use it as a sentinel, and you can use it as. Okay, there's too much talking. Okay, please. One person talks again. And if you want to talk, again, I know I say this every day, but I'll say it again. If you'd like to talk, you're welcome. You just please nod inside the room. All right, let's keep going through this. Okay, Alex? Okay, so example, you can read sales data from a file and calculate the total sales. So let's say you've got this file full of data. Here's a number of lines of data. You wouldn't necessarily need this, but you'll see in this program it does need it. The part number, the number of parts sold, the price of the part, the total price number, right? Price times the number, so that's all the money that they made. So there's that text file we just saw it. This I own the NIF, this is actually lecture 2.8, which is coming up. That's the one I said yesterday. I think you could do 2.8 right after 2.4, because it's about reading and writing. But anyway, he's got it in there. So. All right, so we've got a counter, account, item number, amount, unit price, total cost, total sales, good business file. Okay, what is this command? Let's pause it here, just don't go too far. So this command right here, what is this command doing? It's an input file stream, right? So this is typical in the real world where the data, we don't want to type the data in every time. We've got a file full of data and we just want to read it. Somebody else probably made this file for us. So here's the file. Now this file, when it's stored on the computer, it has a certain name. According to this statement, the name on the computer is salesdata1.txt. So there has to be a file in the same folder that you started C++ from that has this name. But inside the program, you can have another name. You get to make up whatever name you want. So this one's going to have the name data in. Okay, everybody understand that? It's the same information, but there's two different names for it. One is the name that's stored in the folder on the computer. The other one is the name that's used inside the program. Okay. Now data and count. So this is telling it to read the count. So it reads that first number, 6. It says total sales equal to 0, counter equal to 0, and then it writes, this is called a header, right? Table headings. So it's going to print numbers underneath these words. Okay? Okay, so now here's the logic of while. We talked about this before. While has a pair of parentheses, and inside of that is a Boolean operator, true or false. As long as it's true, it does everything inside the while loop. If it's false, it kicks it out past the while loop and starts down here. Okay? So he put in while the variable counter is less than count. So remember, on the previous slide, what did he set counter to? I think it was 0. Count, he read from the file. He read that number, so the file is telling him how many lines of information there are. He read the number 6. So as long as counter is less than 6, it's going to execute this. Okay? And what does it do? It goes to the input, and it reads 1, 2, 3, 4 numbers. 1, 2, 3, 4 numbers. How does it know they're separate numbers? Because there's a space in between them. Okay? And this while, yesterday something I said was, I thought you should use the tab key. The tab key was probably used to create this file because the numbers are nice and nicely lined up. It's easy to read. They're not just random. So it's not like there's just one space or two spaces. There's a nice gap and then a column, a nice gap and then a column. Okay? So probably that was made with a tab. Okay, so it reads these 4 numbers. Then for the output, it starts, these commands you'll see these commands in the IO and NIM lecture 2.8. So let's not learn too much about it, but this is to write the output. It calculates the total sales equal to the total sales. Back it up. So here's one of those statements that doesn't make algebra sense, but it makes computer sense. So it adds more to the total sales, the total cost of each cycle gets added to the total sales, so the number keeps getting bigger and bigger. Every line takes this number, that's the sales of that part number, and then on the next pass through, it's going to take that number and add it, and then that number and add it, so it adds up the total cost, At the bottom, counter plus plus, right? So it adds 1 to the value of counter. This statement is sitting by itself, so if you remember yesterday the fun we had with whether or not plus plus goes on the left, on the right, what's the difference in logic? Actually here it doesn't matter because this statement only does one thing, and that's add 1 to the value of counter. So this statement will be exactly the same as plus plus counter because it doesn't matter which, right? So, okay, so it adds 1 to counter. Now remember, it's do while. So it does it as long as this is true. Counter started at 0, now counter is 1. So it comes up here, 1 is less than 6, it does it again. Counter is 2. Counter is still less than 6, does it again. 3, 4, 5, that's the last time. When counter gets to 5, that's the last time. Then it adds to counter, comes back up here, it's not less than. 6 is not less than 6. So on that last time, 6 is not less than 6, it does not do this. It cuts down to the bottom. Everybody understand that? You can accomplish this exact same logic with an if statement. You can have an if up here, and then you have a go-to statement down here that sends it back up. But the beauty of while is it's built in. You don't have to put that go-to statement. Okay. And then one more output line and then the end. There's the output. Prints it all out. It adds up that last column, the total sales. Okay, so I want 2 points about that example. I'll just make 2 things, well actually 3 things I think you should pay attention to in that example. The main thing is the logic of the while statement. But the other 2 things are the formatting of the input file, how nice it looks because it's nice to tab. And also the special formatting of the output, so that when it writes a nice table at the end. It's nice little heading. Okay. Sentinel equal to 999 here? Let's see where it shows up again. So now it's starting to read. So now the while loop criteria is the item number not equal to Sentinel? All right. So what's different about this input file than the last input file? Yeah. In this logic, right? It reads the first pass through every time. It reads a part number. Okay. Now all the part numbers have the same format that begins with 10, something like that. The Sentinel is set to 999. So the idea here is there's no part number 999. So every time that it reads a part number, it checks to see is the item number not equal to Sentinel. If it's not equal to the Sentinel, then it does this. And only when it finally reads the Sentinel number, then this becomes true. I'm sorry, this becomes false, and then it goes to the bottom. Okay? So what's better about this than the last example? Who recognizes there's two different logic ways of controlling how much data it reads out of that file? In the first example, what did it do? Here's this box of data. The first example had 6 up here. The second example has the same data, but it has 999 down here. What was the logic difference? In the first example, it read this number. Then it put a count on the while loop. And every time it passed through, it added 1 to the count. So it went through, and it went through again. And when that count got up to 6, it quit. So in the first example, this number has to tell it how many times to go through. Now let's suppose that you have a big file full of all kinds of data. Maybe lots of people are entering different sales data. Maybe you have 100 different salesmen, and they're all entering lines like this. So the file is getting bigger and bigger and bigger. In order to use this logic, you still have to count all those lines and know what that is, and make sure this is the right number to read every line. Compare that logic with this logic. This logic just keeps reading the lines, one after another, after another, after another. It keeps going until finally it hits 999. Then it stops. So with this logic, you don't have to know how many lines there are in advance. It doesn't matter. It'll keep reading forever until it hits 999. So this is really a lot easier. This one you have to know in advance how big it is. This one you don't have to know. When it gets to the end, it'll figure that out on its own because of the Sentinel. Everybody understand that?
What if the data gets lower than 999?
Well, if it gets lower than 999, that won't matter because the logic is item number not equal to Sentinel. It will only stop when it reads 999. Okay. Now, if your inventory, maybe this is something that Robert's business maybe probably has logic like this, right? If the inventory numbers have a certain format, like in this example, it looks like they all have at least 5 digits. So the number 999 can't possibly be a part number. It doesn't even have enough digits in it. That could be a bit sensitive. You might have to change the way you do the inventory so that your numbers are predictable like that. That way you can be sure there's no 999. If you have random part numbers, any number, then maybe by mistake you choose a Sentinel number that's really a part number and it stops the program up here somewhere because there happens to be a part called 999. That's not what you meant. You don't mean for it to stop up here, only at the bottom. Okay, any question about that? Have you ever put in, let's say you're doing your, you call your mobile phone to retrieve voicemail, and you have a PIN, right? You have to put in the PIN, and at the end of the PIN, on my mobile phone anyway, when I tell my mobile phone my PIN number, at the end I have to put this in, right? pound sign to tell it I'm at the end. Does your mobile phone work like that? Yeah, so what is this? It's a Sentinel, right? When you put a password into most of your computer programs, what does it tell you for your password? 8 to 20 characters. What's the Sentinel for the password? Some kind of a space, right? There must be, it reads a space at the end. Or maybe carriage return, when you hit the return button, something like that. But your password could be anything from 8 to 20. So beginning with number 8, number 9, number 10, number 11, depending on how long your password is, the program has to have some way to know this is actually the end of your password. This is where you mean the end of your password. So it's using Sentinel logic. That way your password could be 8 long, yours could be 11, yours could be 14, yours could be 9, mine could be 20. They all work. The computer can figure it out, right? But it's using a Sentinel that tells it, oh, this is the end. Maybe not okay, this is the end. All right, any question about that? So I think Sentinel is really, really clever. It's a really good way to do it, especially if you have a data file that when you start out, you're not really sure how big it is. Because if you use count, if you use the count logic and you count the number of loops, you have to know in advance what that number is. If you use Sentinel logic, you don't have to know. It'll just keep going and going and going until it finally gets to whatever the Sentinel is. In this case, he used 999. Okay, let's go. Okay, so now this is something a little bit later, slightly different logic, a while loop. Maybe it's good to go back for a minute. Let's just read the instructions out here. Okay, so we have a loop, and the loop continues until the program fails to read new data. Okay? So the data file is the same data file, but now it's just data. So this is a third set of logic that can do the same thing, or a similar thing. Just the data. And there's no 6, there's no Sentinel. So how does this do it? The way this does it is, we've got the loop ends when the program fails to read new data. So we keep telling it to read, but it gets to this line, and there's nothing there. That's how it knows to stop. Right? Let's see how the logic is. So he put name. There's this dot fail with the 2 parentheses. You have to use that, but you can put whatever name you want here. Okay, let's say Ted. So Ted dot fail. That's the command. Okay. So that's an input command assigned to the data file. And name dot fail is true when data is not read. It's false when data is read. Okay, now let's look at the program. Okay, so it's reading the beginning. It reads in the first line of data right here. Okay. There. Now while the data input, right, that's the name of the input file, while that dot fail. So this is going to be true when the data is read. Right? And when the data is not read, it should have the dot in front of it. So it checks to see if it's reading data successfully. If it reads the data successfully, it's correct. Okay? Maybe we better go back and look at that one more time. Just point something out. There's a nice piece of Boolean logic in here. Well, maybe it's not so nice. It's actually sort of arbitrary. What is this Boolean operator? Not. Okay? And when does the data input fail? It fails when there isn't any data. So, if there's no data, this is true. And not true is false. So if it reads data, it doesn't fail. So this is false because it doesn't fail. It's false. And the not makes it true. Okay? Can you hear that one more time? Okay. This dot fail added to the end of the name of the data file, that's a function that when it goes to read data, if it reads the data, it's successful. That means it did not fail, right? Fail means not successful. So this is true. Fail is true if there's no more data. Okay? So if there is more data, this is false. Now, that's the Boolean not operator. So this says not false if there's more data. So while this thing is not false, it means there's more data, so it keeps reading. And when it gets to the end and there's no more data, then the fail becomes true. Not true becomes false. This is now false, and it puts the control past the end of the while. Yeah, that'll make smoke come out of your ears. I said the other day, smoke comes out of my computer when it's working too hard. So when you think about this, smoke comes out of your ears. Okay, does everybody understand this logic? All right, so three different ways of reading a lot of data from an input file. Right? The first way, just to remind you of the logic, the first way says, I'm just going to put a number up here that represents all of the lines of data I'm going to read. It's a counter, something that counts. So read 1, read 2, read 3, read 4, read 5, read 6. I told it to read 6. When it gets to 6, it puts. That's okay if I know exactly how much data I have. That's okay. This one is a little bit better, a little fancier. I put a sentinel in here, like a guard. The guard is at the very bottom. He's looking up above. As long as it's reading more data, it's fine. But when it gets here and it reads this number, that tells the computer you're out of data. Okay? As long as this is the last line, and as long as that number isn't in the first column above, this works fine. The third one has this command that knows whether or not there's any more data to read. As long as there's more data, it keeps reading. When it gets to the end of the data, it quits reading. Right? That's this fail. Dot fail. Okay. Next. All right, let's take a look at exercise 2.6. See if we're ready for that one. Is this fun? No? It's cool.
Because the last one is had more the previous like the central.
Yeah, let's think about what's bad about each one of these. Let's see if we can come up with something, right? Okay, so the first one we've already said it a couple of times. What can go wrong on this one? You put the wrong number, right? You don't know how much data you have, so you put the wrong number. Or maybe you always get the right number, but you only get the right number after you spend a lot of time to count the lines and figure it out, so it's a nuisance. What can go bad here?
The number is right in the middle.
Yeah, I think it's something that you should be able to control. Like you could choose for your sentinel value a number that actually shows up in here by mistake, so it stops too soon. That's if you're not clever about choosing a sentinel. What can go wrong here? What can go wrong in this one?
Only no data.
Yeah, you could. It's something that you hope wouldn't happen, but I said one advantage of this file is suppose you have 100 salesmen all over the world, and they're all sending in the same lines of data, how many parts they sold. So you just keep adding it into one big file so that your computer can calculate the total sales. So the nice thing about this one is, as long as nobody uses number 999 for the parts, it'll just keep going until it gets to 999. Now, suppose with these 100 data files that are coming in of everybody's sales, when you add another file, sometimes you're not careful and you have a extra return, which means you get a blank line in the middle of the data file. There's lots more data, but there's a blank line. This one will stop on the blank line. Right? This one won't stop on the blank line. This one will only stop when it sees 999. Even if it's a blank line, it keeps going. Because the logic for this one says, if it's equal to 999, stop. As long as it's not equal to 999. So a blank line is no problem here. Okay? So they all have, in theory, they can all do the same things. And also, in practice, where it counts, they can all fail. But the way that they fail is different. So it's up to you to decide what failure mode you think is not very likely in your case. Tricky. Now you like the second one. I kind of like the second one too, I admit. So, okay. All right, let's see what we got here. Okay, you're going to write a program to calculate the weight of part of your college football team. This is American football, not. In the U.S., we use the word football to mean a different game than soccer. This game we call it soccer. The rest of the world calls it football. But we have another game that we call football. So this refers to American football. Okay. And by the way, football makes perfect sense in this game. Yeah, so our version of it doesn't make sense. I'm not saying it makes sense. Okay. Okay, so here's what you're going to do. You're going to get. Oh, I guess I'll have to give you this file. I don't think you have it automatically, so I'll find this file. You're going to get a file. It's going to have 2 columns and 20 rows. 2 columns, 20 rows. So that's going to be data that you're going to read. The first column is the player's number on the jersey. And the second column is weight. In American football, it's important how heavy players are. And some of them are pretty big, like 150 kilograms. Yeah. All right, so this weight, I think these numbers will probably be in pounds. And a pound, 2.2 pounds, or 1 kilogram. Also, by the way, it's obvious. If I were learning English, this kind of thing would be very annoying. But the abbreviation for pound, the word pound, doesn't look anything like it. It's LBS. That means pounds. Did Louis teach you that? No, that's pretty obscure. That's not a normal thing to learn. Okay. So you're going to create a program that reads that data, and then your program will determine what type of player a data row indicates. Okay? And the average weight of those player types, and the players listed in the text file. So let me just mention, just like in this kind of football, there are certain positions on the field that's a different type of player. There's a forward, a center, defenseman, right? In American football, when the player gets a number on his uniform, usually the number goes with the kinds of position that he's playing in. But you can have a lot of players that play in the same position, so there's a range of numbers. So they don't all have the same number. But for instance, there's a number between 0 and, well, not 0, you usually don't see that, but 1 to 10 might be used for a certain kind of player. 11 to 20 is used for another kind of player, and so on. So, when your data file is when you're reading this data file, the first column is the number of the player. According to that number, you're going to have to sort them into what type of player they are. Okay? All right. You have to this program is only going to require you to split them into 3 different types. One type is called a lineman. One type is called a back. And the other will be anybody else. Okay? Use if, else block to do that part. Okay, all numbers between 1 and 49 are backs. Numbers between 50 and 79 are linemen. Between 80 and 99 are all the others. Okay? Okay, so you're going to read a player's number, and you're going to have to figure out which kind of player he is using if, else if, and else. So let's see how this is going to work. You want to know is his number between 1 and 49, 50 to 79, or 80 to 99. So let's assume that up here you get his number. I'll call it number. So somewhere up here you grab his number from the data file. So tell me about your logic. What do you want to put? How would you like to start here? Less than 49? 50. Okay, so you can say if number is less than 50. In that case, what kind of player is it? A back? Yeah. All right, now what about this one? Okay, at this point, you already know that it's at least 50. You already eliminated everything below 50, right? So you can do this, right? It's less than 80. Then its type is lineman. And underneath else, the type is equal to other. That's a logic structure that would work, right? Let's try doing it some other way. Let me change this. Suppose that's true. How would you change the structure? Okay, this is no longer right. Right? If it's bigger than 50, he can still be one of these two, right? So I'm going to put another if inside here. If number is greater than 80, let's say. If the number is greater than 80, then the type is other. Then you can put it else here, and this type is lineman. And then this type down here can be back. That logic also works.
And then we say that is maybe 9 grand or type. Put that one, that is 80.
Put 80 up here this time? Did you say here?
And I mean, we put the if number as we have maybe something. We have to be specific in the if
Yeah, like an even or odd or something? Yeah, we could sort them even and odd, right? We could change, but let me just point out, we could do this. I could put this, right? That's a Boolean operator. So the command doesn't look like that. It looks like this. I'm sorry. I guess it goes. Right, less than or equal to 49 is the same as if number is greater than, is less than 50. These two are the same. In theory, this is checking two things. It's checking to see if it's less than 49, and it checks to see if it's equal to 49. In theory, this is only checking one thing, is it less than 50? Okay. Any questions about it? Sorting into these three columns. The point I want to make is this. I just showed you two different structures. Well, you did the first one, then I did one. We did two different structures that would sort into these three numbers. I'll bet if you go home and you think about it and you write out the structure, I bet you could come up with at least 5 sets of if, else, if, else. 5 of these kinds of structures like this, at least 5, that would accomplish the exact same thing. Right? You can start off by seeing if the number is less than 49. You can start off by seeing if it's greater than 80. You can start off by seeing if, for instance, number is greater than or equal to 50. And, right? That means and. Number is less than or equal to 79. Right? That statement. Then you wouldn't even need an if. You wouldn't need an else. Because now you can say right away, this type has to be line in. Right? So there's lots of different ways to look at it. What's up here? Okay, we're good. So, all right. So the first thing you're going to do is you have to decide what kind of player it is. We just talked about that. All right. Determine player. You have to use a counter. Use a counter to keep track of the number of each type of players using the plus operation. Okay. So back over here. Let me take this stuff off. Let's go back to our first statement. This should be if number is greater than 49. Okay, so here's our type equal to line length. So then we would want to have a statement like plus count. Let's say count L for line length. Here, if the type is other, we need a plus count O for other. Down here, a plus count B for back. So you have 3 different counters going. Counting the linemen, counting the others, counting the backs. Okay. Use other variables to determine the total weight of each type of player. Okay? So, also in this place where you sorted them out, you want to have something like weight equal to weight plus, and then whatever the latest weight of that particular player is, which is column 2. Right? The weights are in column 2. So use column 1 to get the number. That tells you which category to put them in. Then column 2, you have to keep adding it together. Like total sales, you're going to do total weight. How much meat do we have? Okay. When you reach the end of the file, stop the while loop. Use a counting option in this program. And stop after reading the 20 lines of the file. So he wants you to use this logic, right, where you count the number of lines, and when you get to 20, you stop. When all the data has been read, calculate the average weight of each group of player types, and then the average weight of the entire team. That's all 3 put together. Print the results to both the screen and to a file named average weight. All right, so this is fun. This is by far the most complicated program yet. You're going to read this data file. You're going to sort them into 3 different types of players. Inside of each type of player, you have to keep an accumulated weight. You also have to count how many players there are. Then when you get to the end of the file, for each of the 3 types, you have to take the accumulated weight and divide by the number of that type of player to get the average of the weight of that type of player. Then you also have to add all the weight for the whole team, divide by all the number of players to get an average weight for the whole team. Okay? So there's a lot of things to count, a lot of things to keep track of, a lot of things to calculate averages. So this is going to be this is probably going to be, I don't know, maybe 50 lines. Especially if, like good little programmers, you put a lot of comment statements in there to remind yourself what it is you're doing on each line, so that when you look at the program again a week from now or a year from now, it'll still make sense to you. You'll remember what the logic was because you wrote it down for yourself. Okay, next thing. do the same thing, same problem, but instead of using a counter to decide how much data to read data from the file until a data failure. So do the same thing, but with this kind of logic for the reading. Okay? Okay, go ahead, Alex. Just scroll down and look down. Yeah, print out the same information. And then you can do these two other examples from section 2.6, a wild factorial, wild, big, small. So you can look at those on your own, a couple more examples. Okay. Any questions about this? So I'd like you for Monday, 2.7, 2.8, 2.9. And definitely do exercise 6. Definitely do this one we just talked about. I think if you can do this exercise, you're in very good shape. I also think it'll take a little bit of time. You have to really concentrate on the logic. But it's good. It's good practice. All right. Thanks. You can ask me questions if you got them. Okay.